And yeah, and I'd like to welcome all our friends, participants, colleagues to today's seminar on optimization. It is my great pleasure to introduce our speaker today, Darinka Dentcheva from Stevens Institute of Technology. Darinka Dentcheva was born in Bulgaria, and she was a member of, or probably still is, of the Bulgarian Academy of Sciences. And then she was for 4 years, 3-4 years affiliated with the Humboldt University of Berlin. And she was a physics scholar of the Rutgers University in New Jersey, and then moved then to Lehigh University. And since 2000, she's affiliated with the Stevens Institute of Technology, where she's since 2007 professor at the Department of Analytical Sciences. Darinka Dentcheva, our today's speaker, is an expert in many areas of mathematics, optimization, complex analysis, working on vector optimization, on statistical methods, of course, on static optimization. She is serving on the board of important journals in the field. And I'd like to mention here the SIME Review. So it is my big pleasure to welcome her. Thank you for accepting our invitation. The floor is yours. You have 45-50 minutes for a talk.
Thank you. Thank you for the kind introduction and for inviting me to this seminar, the opportunity to present this research to our colleagues. Also, I would like to advertise, since you mentioned SIME Review, please consider submitting also interesting topics that you think are good for educating students, but not sufficiently covered to SIME Review section education. Okay, so I'm advertising the section. So there are many things that are not covered in standard classes and are relevant for the research that we are doing. It would be great if we have some introductions written by experts in the field. So currently, oh, just a second, I will start my iPad. Okay, so currently I plan to discuss with you a rather general question, which arose in the context of multi-stage stochastic optimization problems, in which we would like to consider more general, quite more general setting from the currently available literature, in the sense that we would like to consider objectives that are nonlinear in probability, okay, suitable for risk functionals, and also nonlinear dynamics. So the current theory was for nonlinear dynamics and for involving problems that are not all, but mainly nonlinear in probability. So first we consider a general setting, and I will recall also some notions that we shall use, like the composable sets and subregular multifunctions. And we base our theory on what we call causal operators. These are very well defined for deterministic dynamical systems. For stochastic systems, we introduce a specific notion which is good for us, and then I will present optimality conditions for such a multi-stage optimization problems, which have typically in our area 2 different formulations. I'll discuss this in due course. Okay, so what I'm presenting is based on the paper that I have given here in green, it can be also downloaded from ArcSys, a version of it. So the formulation is with the decisions that are in LP spaces. So we assume that the probability space is given with the P that can be also equal to 1, but not to infinity. So it's not necessarily a reflexive space because L1 is included, but generally L infinity, we don't consider an L infinity for now. So we minimize a general such objective functional, which we consider, we shall assume Lipschitz and continuous. And our dynamic will be described by this inclusion. Okay, so here is a little bit the general setting for a moment, but then we shall pass to a more specific one. So F is a nonlinear operator from LP to another space, which will be also for our application will be also LP space with realization though in different dimensions. So the decisions have random vector functions, if you wish, or realization in Rn. Well, this can be in Rn. So we have also these two sets. Okay, so we take the point of view that these are multifunctions from the probability space from omega to Rn or to Rm respectively. And N is a subspace of LP. So you will see later this is necessary to express the requirement later in the sequential decision models that the decisions have to be non-anticipatory. So that this will be certain measurability requirement later. So for the setting that we shall discuss, this nonlinear operator F will have such a form. Okay, it will be given by a superposition function. So little f, which depends on a random element and is random by itself. Okay, so this type of a function. This will be this will describe the dynamics of the system. So just a recollection of things that are generally known. We shall work with the contingent cone. So probably most of the audience knows the definition of a contingent cone, so I'm not going to spend the time on explaining it. We shall deal also with set that we shall call that will be derivable. Okay, this notion was introduced by Oben and Frakowska. This means that the contingent cone actually is a nicer set, so it contains, so the limit of this distance quotient exists. So if you look at the contingent cone here, we have all sequences, all accumulation points of such sequences which are built from the, say, elements x tau minus x divided by tau. So accumulation points, and here we say that these sequences also have for every such if you have sequence, you have also not the set of accumulation points coincides with the set of limiting points. So this is a derivable set. So also a subset of LP is called decomposable if it can be represented by such measurable multifunction, and the set consists of all elements of LP which are such measurable selectors of this multifunction. So they belong to this multifunction almost surely. So for example, typical constraint is that say you have x greater than or equal to 0 almost surely, where x is an element of LP. So this type of constraint satisfies such a representation. So a known result is that a set is if a set is decomposable, then one can represent the contingent cone. So it's also decomposable, the contingent cone, and one can represent it pointwise. So if you consider for each, I will say, realization of X and the set A, okay, so the tangent cone to the finite dimensional realization of A at the realization of X, then it contains the elements which are in the contingent cone as elements of X are such that they are pointwise also tangent direction to the realization of A at X. So this is decomposable also, the contingent cone. And this is not difficult to show that such a nice property. Then if a cone is decomposable, then its polar cone is also decomposable. So the polar cone is a standard definition, which I have repeated here, and specifically since we deal with we focus mainly on LP. So the polar cone will be in LQ, and here is the standard definition, so you know. So in this case, the polar cone of a convex decomposable cone is such that for every omega, this is the polar of the corresponding cone K considered at omega. So again, pointwise, which is a nice property because it allows you to reduce the infinite dimensional aspect to finite dimensional considerations. So what we call here subregular, it's a little bit, maybe not exactly what is in the literature called subregular multifunction. We are mainly interested in a situation in which we have a say multifunction from space X to space Y, some Banach space. This can be, both can be general Banach spaces for the purpose of definition, but for our further analysis, we consider the LP spaces, and we particularly look at the point X, which contains 0. Okay, so 0 is an element of the image of this multifunction. So we call this multifunction subregular at a given point for which 0 is element of the image. If in the neighborhood of this point, we can find such a Lipschitz constant, okay, so constant positive, so that for every point which is close to the point x hat from which we start, of course, x hat will, point x may not be such that zero contains, the zero is contained in its image, but we can find another point, x tilde, to return to the situation that the zero is belongs to the image of at this point, and the distance between this correction and the point x is bounded by the distance of zero and how far zero is to the image of the multifunction for x, multiplied by the constant, obviously. So if we should consider such an inclusion, for example, okay, then the multifunction can be defined by the difference between, so there will be some point y here, a point, and the set y. So if y is LP space and f is Lipschitz continuous, and y, this y, okay, so this y is a nice set, closed convex set, then subregularity at our condition at the point x hat amounts to such a known condition of regularity, but just locally around x hat, okay, such, and just the issue is with the closeness of here of this image of zero. Or equivalently, this is can be characterized by the notion that was first introduced by Robinson under the name upper Lipschitz property. Is also used in the same way in the work of Dithard Klatt and Bernd Kummer in their book and most of their works. Okay, so, but more recently it's established like calmness. So if we consider such a multifunction that contains all arguments, so that f of x belongs to y minus z, where z is here the perturbation. Okay, so you need z to return to y. So then this notion subregularity that we defined can be considered as the calmness of this multifunction at the point of zero and x hat. So this is in connection to other to previously introduced notions. Actually, we were inspired by the work specifically of Dithard and Klatt and Bernd Kummer and others on subregularities, and Dentcheva, Rockefeller, and so on subregularity. So for causal operators, so what we shall call causal operators. So we have a probability space, and let's say we shall, since we want to consider dynamic systems, we have a filtration which is associated with the sigma algebra F in this probability space. So now consider the LP spaces in which are associated with the elements of the filtration, and the LP space is Y, again with the elements of this filtration. So the first is, of course, images in Rn, and then the second is with images in Rn. And okay, this is just a piece of notation. So the entire space capital X in which we shall transfer our problem. Okay, so the problem that I started at the very beginning. Okay, so I said capital X is LP, but here we start considering problems that are such products of LP spaces associated with this filtration, and Y is the same way. It's a product of LP spaces. And of course, for every little time t, we consider the intermediate space, okay, from 1 to little t. So the operation F, the operator F, which is associated with the dynamics, which describes the dynamics of the system, is, we shall call it causal, if these little functions exist, okay, that tell us describe the operator by using the trajectories and trajectories from 1 to t for each elementary event here, and can be also random by themselves. Okay, so such a superpositions, and we assume they are measurable. So this expresses, why do we call it causal? It expresses the fact that the dynamic only depends on the information that is available up to time t. That's why we call it dynamic. So it doesn't depend on any future decisions, but only depends on the decisions that are taken up to time t. So this is the only explanation. And we shall assume in addition that we deal with such causal operators for which some regularity assumptions are imposed here. And one assumption is that with respect to the second row, so if some here element is given, okay, so trajectory is given here, and we just consider f as a function of the second argument, then this is a random variable. So it's an element of LP. So this is the first. So for each trajectory, this would be an element of LP. So this is an absolutely natural assumption. Then additionally, we assume that with respect f, the little functions f, for every fixed elementary event omega, they are continuously differentiable with respect to the first argument. This is also not a strong assumption. The second assumption, though, is this is a bit stronger assumption, okay, that the Jacobian, okay, for this function, for the little ft function, that it is bounded, so uniformly bounded, actually, almost sure. So this is a bit strong assumption, but is necessary for further such Lipschitz behavior and to analyze the system. So now we investigate differentiability of this causal operator under the assumptions that we have, and we can show that under this assumption, the causal operator is cathode differentiable. So if they so these are assumptions. These are assumptions again that are basically pointwise assumptions. Okay, so pointwise assumptions, and we obtain cathode derivative for the operator, which is infinite dimensional object. So now we have to deal with compositions, since we have this nonlinear dynamics there. So if we consider a causal operator and again, with this assumption, I will not repeat it all the time, with the assumption that I just explained, and the convex subdifferentiable function of from LP to R, okay, functional, which is subdifferentiable and convex. Then the Clark subdifferential of this composition can be described. Okay, so this is the composition is subdifferentiable in Clark sense, and we can describe the subdifferential. I mean, sorry, we use the composition is Gateau differential. We use the Gateau differentiability of the of F. F is not just it is more than Clark subdifferentiable. Okay, so F is Gateau differentiable, and the convex functional is Clark subdifferentiable. So usually to obtain differentiability of composition in such problems, so far people have assumed Frechet differentiability of this operator F. So our here result is about the weaker assumption. So assumption A implies Gateau differentiability, and only using Gateau differentiability we still can obtain subdifferentiability of the composition. So we need this mainly.
Sorry, Darinka, may I ask you? Do you really need a rho to be convex?
Sorry?
The function rho. So is convexity essential? So the formula should work also for a locally Lipschitz continuous function, I guess, no?
No.
Okay.
No, we have used convexity in the proof.
Okay, thank you.
So actually, let me tell you, probably it's possible, maybe it's possible, I'm not sure. I frankly speaking, I don't think it's possible to extend, but it's possible to extend probably to, it's still possible to abandon convexity, but probably to weakly convex. I don't think it's possible to go very far. To just to Lipschitz. I'm not sure it's possible to go to Lipschitz. We needed this. We actually were focusing on differentiating this because it's a penalty function to the constraint. So we actually first formulated the result that we can calculate the subgradients to this composition, well, the distance function and the causal operator under Gateau differentiability assumption for the causal operator. So
in fact, I was not saying just Lipschitz, probably regular Lipschitz. Yeah, like of course there is regularity is also important.
Yes,
but usually
yes,
these
yeah,
formulas.
Yeah. So yes. So then we realized that actually there was nothing special that we used about the property of the distance function. So for every convex function, this would work also.
Yes.
So, but as I said, okay, to derive the optimality conditions, we wanted this penalty function. And so first we attempted to show that that we can, under some conditions, we can obtain Frechet differentiability. Then we realized that this is actually almost impossible. So we have an example here, which is very simple, which is not even a real superposition, because if you define the operator, so this is but P is equal to 1, so L1. One can have also for other p's, but it's sufficient to consider L1 at the moment. Omega is just a 0, 1 with Lebesgue measure. And this function is just like a Huber function. So it has, it is between 0 and 1 quadratic, and then goes up to linear, like this. And so we found out that this function is not so the x squared is not differentiable with 0. It's not Frechet differentiable at 0. So it's very little hope. This is, I mean, if you take the x squared, and even this is not Frechet differentiable with the here I have a construction. Okay, so this is a random variable that this is 1 or 0. So 1 is between 0 and 1 over n, and you can calculate then the differential quotient. So according to our result, this is this operator is Gateau differentiable, and the Gateau derivative one can calculate is equal to 0. If it was to be Frechet differentiable, then both should coincide. It should be 0. But if you calculate the limit here, so if it is, it cannot be 0 because you obtain a sequence that is basically with a norm 1 from this xn. So therefore, for this, since this sequence doesn't have the same limit, so it's not Frechet differentiable. So it's very little hope to somehow connect to other results that assume Frechet differentiability for this setting, okay, for this setting. So now specifically to multi-stage problems, the first formulation is such. So we have objectives that take all decisions from the beginning to end. So for example, this can be dynamic risk measure. The second formulation is a causal operator to belong to some set which changes in time t. Okay, so this is a causal operator, so depends of all the trajectory, all the history from 1 to t. Okay. And we have also local constraints for each time, for almost sure constraints. So now how the assumption of subregularity has to be formulated for this particular problem. So this is the following. So we look at the function little f, which describes the causal operator. So little f describes the operator by taking the decisions from 1 to t and omega. So if this is the current decision at time t, these are the ones, the history, okay, from 1 to t minus 1. This is a time t. A realization for particular omega, okay? So this is pointwise. If this belongs to the set y for this elementary event, so yt is here for this elementary event, and xi is satisfies for this elementary event this inclusion, then we consider this system basically finite dimensional systems for every simple event. And for this finite dimensional system, we require the subregularity assumption. So this is basically assumption, what we call subregular recourse, and require that the problem has subregular recourse is an assumption which is pointwise for every simple event. So it is applies to finite dimensional systems. And here, so for this such a decision, you know, that the standard way of formulating the subregularity is to say, okay, so if you have a deviation here from this psi eta, then you can find another point so that the difference between the two is estimated by such a distance of the function to the set y and distance of this element, okay, this element to the set x, to feasibility. So distance to feasibility, right? So, but as I say, the formality is just a finite dimensional requirement, which is required for each, which is required pointwise. And if this is satisfied, then we can show that, and of course, the assumption for the assumption A is always required for the subregular, for the causal operator. Then we can show that the infinite dimensional system is also subregular. So this system is then subregular in the sense that I discussed previously. Okay, so the infinite dimensional sense, and then we can apply our result with optimality condition in form of this penalty function and derive optimality conditions for this particular case, which have a standard form. Okay, so standard in the sense, I mean, it's not very standard because this is a new setting with quite a bit of nonlinearity in it, but it's standard in the sense that we have subgradients from the objective function in normal elements, okay, to the set where the dynamics has to belong, and normal elements to the feasibility set for the decisions. And these are the A here are such operators, okay, partial Jacobians for the causal operator up to time t. So each one element here is for the Jacobian or of ft, okay, where ft is this operator. So you have a big operator f, which takes all the little ft's and they are differentiated themselves. Okay, so this is like a product of such little f's. Okay, and they are given by this little f. So so this is one result. This is a necessary condition of optimality. Okay, so the other result is for the case where we do not enforce this causality is not built in the formulation, but we consider for every decision xt, we create copies of it and allow it to be random, so to say, at every time t. And now the fact that it has to be the same. It cannot be random for the time that is already passed, because it has to coincide with what has happened. Is expressed by such a measurability assumption. Okay, so that or rather, should I say that the fact that this is non-anticipatory decision is expressed by this assumption that this is that at time t is measurable with respect to this sigma algebra. So it means that for the elements of the sigma algebra, we have to average appropriately the xt's. They cannot be fully random with as it is assumed in the extended space. So the extended space allows for every time t to use the full sigma algebra, not the sigma algebra that distinguishes between the events of R. So it uses the full sigma algebra. But this assumption then returns to the idea of having non-anticipative or non-anticipatory decisions, and we can work with the bigger spaces. Okay, so they are denoted by tilde, but we have this explicit assumption just to recover the causality or the non-anticipativity requirement here. And the operator now formally can be also extended to have a proper definition on the extended space. So I don't want to go into all details, but so the difference between the previous formulation is that these spaces are bigger, and you have additional constraint here, which is which actually determines a subspace of LP. So this is why the initial formulation was like this. So we have a subspace, and here we have these elements x from 1 to t are still random here. In the extended space, it takes also value in the extended space, and these are in the extended space. So again, we can analyze the formulate again such a subregularity assumptions in the finite for every particular event. So have a subregularity assumption which is finite dimensional, and then derive that this system of constraints that is here is subregular in the infinite dimensional setting, and use the penalty approach again to derive necessary condition of optimality for this formulation. And now again we have what are the elements in the conditions. These are elements which are which is a subgradient for the objective function, and these are all normal elements. Of course, here are the Jacobians, the transposed Jacobians. These are the adjoints of the causal operator. These come from the dynamics, and but these are this lambda, this psi, And these are the corresponding normal elements for the different sets, okay? For the local constraints, lambdas are associated with the non-anticipativity constraints, and this psi are with the set where the dynamic operator has to belong to. So this is the additional like a complementary condition for the non-anticipativity constraints elements. So we can also say what is the general relation between the two formulations. So if we identify objects in one formulation, for instance, in this formulation, then we can obtain the objects, the corresponding subgradients and normal elements in the other formulation by say averaging, okay, for this this G are on the extended space, so we have to average them appropriately to obtain measurable elements with respect to the corresponding sigma algebra from the filtration. And also for this, the same is for these normal elements, for the other normal elements. These disappear, these elements, because of the expectation is the projection, of course, the conditional expectation at 10t is 0. So this is just a first step. So I want to say what we can do further. So first, the advantages, I stressed this many times, that we can verify some infinite dimensional requirements by looking at finite dimensional objects. This is one good thing of this result. We have the Clark subdifferential of composition of the distant function and a causal operator, which allows for exact subdifferential calculating of the exact subdifferential of the penalty function with the system dynamic. And it has the potential of addressing nonlinear stochastic dynamic problems, but we still have to, this is such a general formulation, we still have to work to see how the particular setting, for instance, with dynamic measures of risk or some other settings with the nonlinear dynamics will be what kind of conditions that will result in, and use these conditions also since the Clark subdifferential actually facilitates also methods, so use this condition in methods. So I don't know whether the Kruger-Mordukhovich calculus can be used, but if it could be, it has a potential to have also non-convex functionals. I don't know. This question was already raised, but so far we that's how far we went. Thank you for your attention.
Thank you very much for a very interesting talk. It's time for questions. Jonathan.
Yeah, just a simple question. Would have you been able to get similarly useful results if instead of depending on the entire previous trajectory, you could basically just depend on the previous state, have more like a control type formulation?
Oh, this is actually straightforward if you just depend, because it's actually more difficult to say it depends on the entire history than it's just straightforward.
Yeah, but I was wondering maybe you could have simplified.
It's still not the Markovian, okay? If you are asking about Markov dynamics or something like this.
Yeah, yeah.
This is actually for non-Markovian systems. There may be more specificity if you have a if you more specificity if you have specific dynamics, specific systems. So this is still to be explored. Okay, certainly you can obtain better results if you have more structure. I mean, more specific results may be more useful for some.
Right. I just wondered maybe,
or,
I mean, sometimes, I mean, in more simple stochastic programming, you can kind of exchange these two formulations, right? You can depend on the entire trajectory, or you can basically encode the whole trajectory in the state and use a simpler formulation.
yeah, this is true. You can consider the state, you can encode this and consider as a state the entire trajectory, but
Right.
here is just explicit.
Okay.
Thank you. Jane?
Yeah, can I ask a question?
Sure.
Yeah.
Good morning. Good morning to Victoria.
Yeah, morning. I was wondering if you, in your subregularity, can you use the weaker concept of matrix subregularity?
I mean, this is actually it is not exact. This is not exactly metric regularity, but it's also not exactly. I don't know how exactly it fits to subregularity. To what people say is metric subregularity. So I have not explored it.
Yeah, if you look at the definition, if you look at the definition of the page, yeah, if you here the neighborhood is on X, right? But if you say also that there exists a neighborhood around a neighborhood on the image of the map, then it's weaker.
Actually, this is a one-sided distance. This is from the distance from 0 to this element. This, I think, is a weaker condition.
So this.
So it is at a point. Actually, it's more like calmness rather than as a full metric regularity. But there are so many notions. I tried to explore this, but so many notions about strong regularity, this and that in the different books, and I was not. I didn't have enough time to put somehow complete clarity as to what conditions are necessary to obtain one or the other. Is it exactly equivalent? But ours, okay, so I mean ours, maybe it's not this coincides with some, seems that it coincides with the calmness at this
so
point.
it's not the Robinson one, right? Because for the Robinson is stronger than the calmness. Upper ellipsis is stronger. Here you. Okay, so.
But this is more specific for this one. So yeah, this still needs some clarification. I hope I'm stepping down as a chair at the end of this month. I hope I have more time for research. So
okay, so you think this is the weaker version? I see.
Yeah, I think also with you, it would be interesting to explore in the things that you did with B-level optimization in this context, the same approach.
Thank you, Jane. Are there other questions? Or Jane, do you
No,
have
I'm
another question?
fine. I'm
Okay.
fine. No.
Okay, thank you. Are there other questions from the audience? Then I would like to ask Darinka, so one of the assumptions was this uniform bound for the Gateau derivatives.
Yeah,
So,
this is for the, yeah, here, let me show. This is a bit strong assumption.
yes, but the question is at which point do you need this assumption? Or so.
Oh, here.
Yes. And the question is at which point do you need it? So do you need it for the derivation of the optimality condition? So where is such an assumption?
Yeah, we need it for derivation of the Gateau differentiability of the operator.
Okay. 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 Yes.
Yeah.
Okay.
So for this guy, yeah. So to actually have to pay with something. Okay.
Yes.
So
no, it's clear.
If you want to transfer finite dimensional to
Yes,
infinite dimensional, you have to pay with some uniformity.
Yes.
Somewhere.
Then could you please go to the formula of the tangent cone of the subset of an LP space? So this was a result by Oben-Frankowska. You had at the beginning.
Which one?
So the tangent cone formula. This is the formula you had at the beginning of your talk.
Other direction.
Oh.
This is a very nice result, actually. Okay, then I have here a comment. I mean, what we know is that taking the tangent cone of a set at the point of the interior of the set, we get the whole space. Yeah?
Right.
But for such a set, one cannot expect to have points in the interior. So even if one takes the non-negative orthant of LP, yeah?
Right.
So like LP plus, there are no interior points. But what I noticed that one can use the so-called quasi-relative interior points in the sense of Borva and Lewis to get the same property. So there is a very weak interiority notion which is relevant for LP spaces, for sets in LP spaces. So one, and then one can just weaken the interior to get the same property for this tangent cone. Yeah.
Yeah, I think that in there, if we talk about the same paper, maybe it's not the same. In their paper, you have constraints that are finite dimensional.
Yes, but the notion is more general. It applies to sets in LP space. It makes sense for this type of sets. And this is a very interesting notion, and there is a relation between the formula of the tangent cone and this causative interior notion.
Right.
Yes, but then then also related to this, so the subregularity assumption you made, is this a substitute for constraint qualification? Should be, yes. I guess. Okay.
Yes. Because the main issue is to obtain the intersection of the normal cones to be equal.
Okay. Yeah. And this is probably also related to the fact that classical interior notions play here no role. I mean, and then probably one could.
This is
one could use different notions.
You see, especially in L1, this is a very nasty thing.
Yes.
Okay, so with the interior.
Okay.
If you have almost sure constraints.
But then I guess the difficulty, Darinka, is to verify that this condition is fulfilled. Yeah? I mean,
but that's exactly the point, because we verify only finite dimensional conditions.
Yes. Okay. Yes. Are there other questions? Thank you. Are there other questions? So the probably last question from my side. so then you mentioned on your last slide that some interesting applications would be related to the use of convex risk measures, like in your models.
Yeah.
But then one needs there some differential calculus, and I'm not sure that there are some differential formulas for too many such convex risk measures. No, I mean
this is for discrete time. Okay, I'm not talking about passing to continuous time yet.
Okay.
This would be very, very difficult.
Yes, I agree.
Yeah, you are right. Okay. But you see, young people like you, okay, talented.
Yes, I mean, the topic is very interesting. Yeah.
Yeah.
So if there are no other questions, then I propose to stop here and just thank our speaker again. Thank you for a very nice talk, very nice discussion. So I just want to announce that we will post the slides and the video on the website of the seminar. And to announce that our next speaker will be Thomas Pock from Graz. I would like to wish you a nice week. See you next Monday. Thank you, Darinka. Thank you very much.
Thank you for your attention. Thank you all.